We tend to think the basic building blocks of reality are pretty much sorted,
Hmm.
Matter particles, force particles, done. But what if there's something else? A sort of third way for particles to be. That's what some physicists are asking now. Today, we're doing a deep dive into your sources on something called parastatistics. And these pair particles, we got the classic theory papers, sure, but also some really fresh research from, like, just this year that's shaking things up.
Yeah, it's genuinely fascinating because for decades, this question of what kinds of particles are even allowed seemed, well, settled. You had fermions, you had bosons, that was the menu. But this new work, it's really forcing us to look again. It even challenges how we define particles being identical, indistinguishable.
Okay, let's back up a step. Remind us about the two main kingdoms we do know. Fermions and bosons. So fermions are the matter bits, like electrons, quarks. Bosons carry forces, photons, gluons. And the big difference is how they react to swapping places.
Exactly. It's all about the quantum state. If you swap two identical fermions, the overall description, the wave function, picks up a minus sign. And that little minus sign has enormous consequences. It means no two fermions can be in the exact same state at the same time.
Right, the Pauli exclusion principle, that's why atoms have structure, why we don't all collapse into a blob.
Precisely. It gives rise to chemistry, to stability. Bosons, on the other hand? Well, swap two identical bosons and nothing changes. No sign flip, which means they compile into the same state. Think of laser light, tons of photons all acting as one.
So, okay, fermions are antisocial loners, bosons are super gregarious. Where do paraparticles fit in?
Right in between. They'd obey what's called intermediate statistics. Sometimes it's called statistics of order p. The idea is maybe you could fit, say, p particles into the same quantum state, but particle p plus 1. Nope, it's full.
So, not just one, like fermions, not infinite, like bosons, but a limited number, like a small club.
Kind of, yeah. A quantum state with a fixed occupancy limit greater than 1. That's the theoretical possibility.
But didn't we think these were impossible in our 3D world for a long time? I remember reading about the DHR theorems.
Ah, yes, Doppler-Hag-Roberts. Those theorems back in the 70s were pretty influential. Based on the rules of quantum field theory and relativity, they strongly suggested that in 3 spatial dimensions, you only get bosons or fermions. Full stop.
Leaving just those 2D particles, any's, the ones people are excited about for quantum computing.
Exactly. Any's are a legitimate possibility in 2D. They have their own weird statistics. But 3D pair particles seemed ruled out by DHR.
So what changed? How did they get back on the table?
Well, researchers like Wang and Hazard took a closer look. They argued that maybe the original DHR assumptions were a bit too restrictive. They came up with models where if these paraparticles had some extra sort of hidden shared properties within groups, then maybe they could exist in 3D after all. It sidesteps the strictest interpretation of the DHR constraints.
Interesting, but then there's another twist, right? With Miller's work on indistinguishability. That sounds really subtle.
It is subtle, but potentially very deep. Muller looked at these proposed 3D paraparticle models, like the Wang-Hazard type, and he asked, are they truly indistinguishable in the way quantum mechanics demands? His analysis suggested, well, maybe not fully.
How so? I mean, if I swap two, don't I get the same physical situation back?
Here's the nuance Miller pointed out. Sure, maybe one observer doing measurements might not see a difference after a swap. But if you have 2 observers, Alice and Bob, and they can share information about their parts of the system, Miller argued that for these specific paraparticle models, comparing Alice's and Bob's data could reveal whether a swap had occurred.
Ah, so if the shared information landscape changes, even if my local view doesn't, they aren't truly identical.
That's the core of the argument. True quantum indistinguishability should hold up against any possible observation, including comparing notes between observers. If it doesn't, then something fundamental is different.
Okay, so we have theoretical models allowing them, but also critiques about their fundamental nature. Where might we actually find these things, if they exist?
The most likely place isn't as fundamental particles, like electrons. It's probably as emergent quasiparticles. Think of them as collective wiggles, specific kinds of vibrations or excitations within really exotic materials or specially engineered quantum systems. People are looking at things like Rydberg quantum simulators, systems of highly excited atoms, as places where you might coax these parastatistical behaviors into existence and actually see them.
So maybe not fundamental building blocks, but possible emergent phenomena in complex systems. But wait, there's even more recent work, something about quantum information putting up another barrier.
Yes, very recent work by McConnon, Galley, and Muller proposes a new, potentially universal constraint called invariance under quantum permutations. It's a constraint rooted in quantum information theory. The argument is basically that nature demands a certain consistency in how information is preserved when you swap particles.
What kind of consistency?
It says that the quantum information a system holds about other systems must remain unchanged when you swap identical particles within it. Think of it like the universe keeps consistent records. If a proposed particle type, like these paraparticles, would violate this information-theoretic rule upon swapping, then nature just might not allow it, period, regardless of other physics.
Wow, so it's like an information-based filter that could rule out particles even if other theories seem to allow them.
That's the idea they're exploring. It suggests that maybe the reason we only see bosons and fermions isn't just dynamics or symmetries in the usual sense, but something deeper about information itself.
So where does that leave us? And more importantly, what does this mean for you listening in?
Well, you're basically hearing a live debate about the absolute foundations of reality. Are bosons and fermions the only game in town because of deep information rules? Or could these paraparticles be lurking, maybe not in empty space, but inside strange new materials we can create in the lab? The jury is still very much out. Before we wrap up, just a quick mention of our sponsor. This deep dive was made possible by embersilk.com. If you're looking into AI education or integrating AI, check out Embersilk. It makes you think, though. Frank Wilczek, who won a Nobel for work related to anyons, famously called paraparticles a theoretical curiosity. But this recent work forces a fascinating question. If something could exist according to some physical laws, but is forbidden by fundamental constraints on, say, shared quantum information, which rule is more fundamental? Is the information constraint somehow deeper than the physics itself?
That's definitely something to mull over, a really deep question. And if you enjoyed pondering these questions with us today, please do take a second to subscribe wherever you get your audio and maybe leave us a 5-star review. It honestly makes a huge difference and helps us keep exploring these complex ideas. Thanks for joining us.